Hello dear learners. In the last lecture, we have seen what are planetary magnetic fields, and within the solar system we looked at each planet and try to understand what is the reason that some planets have global magnetic fields and some planets do not exhibit global magnetic field. In this lecture, we are going to discuss about the Earth's magnetosphere. We will look at historical aspects which led us to know that magnetosphere of the Earth is existing or Earth is a magnet, and then we will also see some interesting aspects, or we will look at the structure of the Earth's magnetosphere, various components of the Earth's magnetosphere, not in detail. We will not discuss everything. We will try to understand very important aspects about this structure of the Earth's magnetosphere. So, Earth, we have seen that Earth is a magnet which exhibits a dipole magnetic field. So, the Earth's magnetosphere is invisible. So, Earth's magnetosphere is that region surrounding the Earth where the magnetic nature of this dipole that I am talking about can be felt, or where it can be dominating. So, at the same time, this entire region where the Earth's magnetic field is dominant is like a bubble in the interplanetary space, and this bubble is constantly compressed by the solar wind and the solar wind magnetic field. And the balance between these two pressures will decide the spatial extent of the magnetosphere. So, Earth's magnetosphere may be invisible, but it plays a very important role in making the life on Earth possible by protecting us from the solar wind and harmful high energy cosmic ray particles. So, solar wind, we know that it is primarily electrons, protons and ions which are radiating away from the sun in all directions, and they can, if they can directly enter the Earth's atmosphere, if the energies are sufficient, they can severely damage a lot of our technological assets. At the same time, it may also be harmful for the human life like the way we know it. And in addition, the cosmic ray particles which are coming from outside the solar system, the flux is very large, and magnetosphere is able to shield that cosmic ray particles without entering into the Earth's atmosphere, right. So, the magnetosphere of the Earth is not just the magnetic aspect of the magnetic property of the Earth, rather it is a very important piece in the life or the sustenance of life on the Earth. So, we will learn some fundamental concept about the magnetosphere, which is the most important element in understanding the Sun Earth interaction. So, we see Sun and the Earth, they are coupled with the energy. Of course, they are in the same system, but they are coupled by the energy output of the Sun, and this magnetosphere seems to be the most important piece of this understanding. Okay. So, the Sun is a dynamic star and we actually live in the atmosphere of the Sun. Okay. So, Earth responds to the changing Sun, and that response is also known as the space weather, which refers to the dynamic conditions in near Earth space or in the geospace. So, we can understand this interaction or this connection by many satellites and their observations which are continuously made to monitor the geospace. So, different parts of the geospace are monitored by different scientific instruments that the humanity has put at vast distances from the Sun, at vast distances from the Earth, and the technological developments have demonstrated capability to understand even the Sun from the nearest proximity in terms of the Parker Solar Probe, etc. Right. So, in this lecture we will look at history, a brief account of how the understanding of the magnetosphere and its importance has evolved over the period of time. So, in the beginning we can understand we did not know what magnetosphere is, and imagine a situation, let us say several thousands of years ago, when people, the peasants who used to live in those times, may have seen the aurora and must have wondered what these lights are, and their psychology may have attributed these lights to many things, many divine things, for example. But now at this point of time in today's time, we know what these lights are and what connection is the sun doing for these auroral lights to happen. Because aurora, like the basic definition, is an outcome of the interaction, direct particle interaction between the earth and the sun. So, the particles which are emitted in terms of, let us say, coronal mass ejections or solar flares, they precipitating the energy and releasing aurora is an evidence that whatever the theory that we have built around ourselves to see the planet Earth as a magnet seems to be a solid one. Okay. So, to begin with, we will look at the historical aspects, which will just tell us how we came to know about the existence of magnetosphere and in different ways which have manifested, which further strengthened this basic idea. And then we will look at the anatomy of the magnetosphere, basically the structure. We will look at a cross sectional view of the magnetosphere and try to understand different components in the magnetosphere. Okay. So, it is basically a description of the various regions of magnetosphere. Right. So, at this point of time, it is very safe to say that except for Earth, the terrestrial planets, none of them have an intrinsic magnetic field or a global magnetic field, and Earth seems to be the only planet which has a magnetic field of sufficient strength to be able to deflect the continuous stream of solar wind and even also take care of the extreme coronal mass ejections, etc. And by a chance, Earth seems to be the only planet which harbors life, as we know, at this point of time, right. So, all these things are not mere coincidences. All these things happened in such a way that the final outcome of all these coincidences, if you want to say that, is just the sustenance of life on Earth. Okay. And magnetosphere seems to be playing the most important role in this life. Okay. So, the history of magnetic field, so it has been known since 1600s. The Earth itself is a giant magnet, depending on the movement of compass or anything. So, we since 1600s we know that Earth is a magnet, and convective motions and rotation of the iron nickel core generate a dipolar field similar to a bar magnet. This we have already seen in the last class. The Earth can be approximated to a dipole with the magnetic south pole situated in the geographic north pole and vice versa. Right. So, so you remember this number, since 1600s we know that Earth is a giant magnet. So, what else substantiates the solar wind flow is we can also look at the comets, where in 1600s Johannes Kepler noted that comet dust tails always point away from the sun and made a guess that it may be due to the sunlight pushing the comet dust towards the outer side of the solar system. So, you have to keep in mind that these things may appear very illogical at this point of time in 2026, but with the knowledge that people had that time, it is quite obvious that sometimes this illogical understanding may have been just because of the time that they were living in. The comet's second tail, which looks in blue color, remained unexplained until the 20th century, when the idea of a flow of ionized particles from the sun, which is basically the solar wind, when it was accepted, then people realized this blue tail is because of the ionized particles which are flowing away from the sun, and we call it as solar wind, right. So, that means the magnetic nature of the solar wind or the energetic nature of the particles was the clear reason behind these comet tails always pointing away from the towards the edge of the solar system, irrespective of the direction of the movement of the comet, whether it is moving inwards or outwards, the tail always pointed outwards, right. Now, the experimental evidences subsequently came when Christian Birkeland was the first to predict in 1913 that the sun gives off a steady wind of ionized gas. So, something like an evaporating vapor going away from the liquid which is being boiled. Just like that, sun can be considered as a hot object, and vapor is evaporating from all sides from the spherical surface, and this vapor is what we refer as the solar wind. And Birkeland in 1913 made a prediction that the sun gives off steady wind which is made up of plasma. And the simple, the spherical magnet that he constructed, the Terrella, he used it to show that the plasma is directed towards the poles, causing the aurora. So, plasma, because of the magnetic polarity of north and south, the plasma is going towards the poles, which subsequently give a hint that this is where actually the particles are directed, and this is where the particles are actually getting precipitated, giving off to the auroral emission. So, this image shows Birkeland and his early experiments in 1800s. And then if the particles are being directed towards the poles, so then we should also be able to understand how the particles are being precipitated and how particles are trapped between these two magnetic poles. So, Carl Stromer used Birkeland's results and showed mathematically that particles following a dipole magnetic field line can sometimes become trapped in sort of a magnetic bottle. So, we are talking about magnetic bottle or gradient magnetic field. And if you have a situation when there is a strong increase of magnetic field, it is there, of course. If you consider any realistic magnetic field, the pole strength or the magnetic flux intensity, the magnetic field, in simple terms, its strength will be larger at the poles. So, you are looking at a situation where the particle will increasingly experience larger magnetic fields as it is flowing down the magnetic line of force, and as a result of this mirror force, before entering into the very strong magnetic field, the parallel component of velocity vanishes, and the perpendicular component of velocity will just make sure that the particle retraces its path and moves towards the other side or other pole. Ultimately, because even the other extreme end of this magnetic line of force is situated in towards a magnetic pole, and because these two magnetic fields being very strong, or these two magnetic fields situated at the edges of this gradient, the particles will remain forever trapped between these two poles. So, or we call this as magnetic trapping, particle trapping. Using a simple magnetic bottle experiment, we can understand how it is done. Or if you want to have a detailed explanation of this process, you can refer to the NPTEL lectures on plasma physics, where gradient magnetic field is explained in a completely mathematical way, and how the components of velocity, some components become 0 and some components take care of this reflection of particles, is very well explained. And if you have some interest in mathematical derivations, you will certainly appreciate, and it will help you in understanding. Okay. So, as the particles spiral into a region of very strong magnetic field, charged particles are reflected back along the magnetic field, and this is basically the gist of all that I have said. So, such particles are thus trapped and bounce back and forth between opposite hemispheres, right. So, these particles, now sometimes it may so happen that if you combine the actual tilt of the earth, and then you will realize the concept of day and night or the seasons. So, this magnetic trapping or particle bouncing off between the opposite poles of the magnet gives a possibility for electrons or energetic particles to precipitate into those regions where there is no direct sunlight, right. So, that becomes just a possibility of energy input into the atmosphere without direct input from the sun, all right. And then the magnetic bubble, this entire region where this magnetic field's influence can be felt, is being referred to now as the magnetic bubble. So, the modern concept of magnetosphere, forming by the interaction of neutral solar wind and the geomagnetic field, was postulated by Chapman and Ferraro in 1931. Right. Now, so far we have not seen how this bubble is formed. We are just calling this bubble as the magnetosphere, and by definition within this bubble the Earth's magnetic field is the dominant one. Outside this bubble, the solar wind magnetic field is the dominant one. But so you have to think of a situation suspending an ideal dipole in a magnetized plasma. So there is a magnetic pressure which is exerted by the solar wind towards the towards this dipole magnetic field, or you can say that the dipole magnetic field can exert some pressure which is equals to b square by 2 mu naught, and this pressure is now balanced by the dynamic pressure of the solar wind, right. So, which is basically because of the density of the solar wind and the velocity with which the solar wind is moving. When these two pressures interact, or when these two pressures which are exactly opposite to each other are brought together, then depending on which pressure is larger, the boundary of the magnetosphere is decided. So, boundary of magnetosphere is basically that line or that region where the dynamic pressure of the solar wind, which is because of density and velocity, becomes equal to the magnetic pressure of the Earth's dipolar magnetic field. So, if the dynamic pressure is very large, if you have a very fast solar wind, then this bubble will be compressed, and it can be easily understood that the interaction from the sun is happening in the day side directly, where that is why. So, even if you can create a dipolar magnetic field, so the magnetic lines of force will look something like this. I have tilted the geometry because of the actual tilt, right. So, this is without the sun, this is how the dipole magnetic field is supposed to look like, and when you have sun which is now pushing this solar wind, and if this pushes, the magnetic lines of force will become compressed on the day side and they will become elongated on the night side. This elongation is not as simple as that. This elongation has to be explained by also including the idea of reconnection, which we will talk about in detail in the coming lectures. But so, the basic thing that we have to understand here is that the modern concept of magnetosphere forming by the interaction of neutral solar wind and geomagnetic field is the dipolar magnetic field of the Earth, was postulated by Chapman and Ferraro in 1931, which is pretty much valid, right. And their paper correctly predicted that the Earth's magnetic field would deflect the ionized solar wind, forming a cavity in the stream. So, you imagine a 3-dimensional solar system in which there is a tiny bubble which is called as the magnetosphere, and at the inside that bubble you have the Earth, whose geomagnetic field is actually creating that bubble, right. So, this is just the way in which magnetosphere comes into existence, right. So, if you do not have the solar wind magnetic field, so this magnetosphere would not exist, or this bubble would not exist. Rather, you would have a continuum of dipolar magnetic field decaying as 1 by r cube into the space. So, you would not have everything confined in this bubble. So, this bubble is because of the dynamical interaction with the solar wind magnetic field, right. So, if you go further ahead, there are more interesting aspects about the magnetosphere which are called as radiation belts. So, we know for now that how the particles are being trapped between the magnetic poles. So, they are always gyrating and being reflected from each pole, north to south and south to north. And in the very early stages, in the beginning of the space age, the US entered the space age with Explorer 1 in January 1958, and Van Allen, using his Geiger counter, was able to see that the counter saturates at 2 different altitudes, 2 different L points from the Earth. What does it mean? So, at these 2 different points, there is a huge particle flux which is saturating the counter, right. So, there must be some reason why there is a large concentration of particles at these altitudes. So, that intriguing question subsequently led to the discovery of what became known as the Van Allen radiation belts. We know that in these belts there are large amounts of trapped particles, and these trapped particles form into 2 belts. Actually, we know that there is belt number 1 and there is belt number 2. So, what are these belts? They contain large magnitudes of highly charged particles, right. Now, this was whatever we have spoken about so far is the history. That means, what and all led to the understanding that we have in these times, how it began, how people realized that this magnetosphere is something that is actually there, and how people theorized many theories on how it works, or why these current systems are there and what influences these current systems, so many things, right. So, if you come to the recent times, the many dozens of spacecraft from many different countries have been launched to study the particles and fields that surround the Earth. So, now we know that this environment, this entire geospace is filled with plasma in a way that it is very difficult to comprehend all the types of interactions which could happen, right. So, in order to understand what is happening, how the particles are moving, how the particles are behaving, and what is the influence of the incoming particle flux, etc. So many things. In order to answer all these questions, many spacecrafts were launched into the region surrounding the Earth or into the geospace. So, what are these things? So, we can understand many things like particle energy characterization or the energy distribution, particle counts, many things, how it responds to the solar prominences. So, as new level of complexity is understood, new questions are raised to inspire the next generations of missions, right. So, many things, even the Aditya L1 mission had dedicated payloads to understand the particle fluxes, their distributions, their velocities, so many things. So, for curiosity, you can refer to these payloads and try to see, if you read about these payloads, their descriptions or their mission statements, you will be able to pretty much map all those objectives or mission statements easily with the basic things that we have discussed in terms of the primary structure of the magnetosphere. Okay. And it is also it is going to be very interesting if you can spend some time reading those articles. Right. Now, we talk about anatomy of the magnetosphere. What does it mean? It means the structure of the magnetosphere. So, if you take a cross sectional view of magnetosphere, it is not just particles and magnetic fields. There are many currents, there are many current systems. So, we should understand what is going on in all these regions, only then it will become, the entire magnetosphere will become very clear to you. Yeah. So, the anatomy, what I am referring to is the structure of the magnetosphere. So, the magnetospheric physics involves a large number of regions and sub-regions, all of which with their own special terminology and their own the physics within these regions and sub-regions is entirely different. That is why we name them with so many different names, right. So, each region which will be described separately, and then we will put the entire picture together and try to see, try to comprehend in totality what and all is there inside the magnetosphere. So, to begin with, we first look at what is called as the bow shock. So, what is bow shock? Bow shock is, if you just look at this figure, there are many things within this figure. So, solar wind is from the sun directed towards the earth. What you see here inside towards the left, towards the right actually, towards the right, that you see the magnetosphere, and within this there are these two belts where the particles are trapped, which you call as the radiation belts. So, radiation belts are basically because of the reflection of reflection of charged particles between the poles, and then you see the magnetic field lines to be compressed along the day side. This is the day side, and they are elongated on the night side, right. So, apart from this is the bubble is called as the magnetosphere. Apart from that, you see an yellow line which is basically the bow shock, right. Now, solar wind is a supersonic fluid. It is not supersonic to begin with, or it is not supersonic when it is starting near the sun. It becomes supersonic at subsequent points in the interplanetary space. So, interestingly, the solar wind's velocity will increase as it moves radially away from the sun. Now, if you want to understand why solar wind is a supersonic fluid, and you have to remember at the beginning of everything, solar wind is able to overcome the gravitational pull of the sun, that is itself a mystery. And then this fluid not only escapes the gravitational pull of the sun, this is now being accelerated to supersonic velocities, and the acceleration is still going on even when it passes the Earth's orbit. So, its velocity is increasing as a function of radius, right. So, that is a different thing, but what you have to understand is, before that, the explanation for solar wind's radial flow or its acceleration is offered by Peter Parker. It was in 1958. So, you can read about this Parker's theory of solar wind acceleration in many books, or you can also refer to the NPTEL lectures, which are probably covered in advanced atmospheric physics. Right. Now, coming back, so solar wind is a supersonic fluid, and the Earth is a magnetic obstacle in the flow. So, you have a river of supersonic fluid flowing away from the sun radially outwards and creating this bubble which we call as the solar system, and within this flow the magnetosphere or the magnetic Earth is an obstacle in the flow. So, when this solar wind reaches the proximity of this obstacle, a shock wave is formed between the sun and the Earth. So, similar to the shock wave of a supersonic jet. So, this bow shock is when the fluid's velocity is decreased, and it is circumventing the entire bubble, and in a three-dimensional picture you can realize that this solar wind will just envelop the bubble and go towards the other side, right. So, this is called as the bow shock, and the immediate next thing is the magnetosheath. So, inside the bow shock, the solar wind has been heated and decelerated inside the bow shock. Because of the compression, the solar wind is heated and decelerated. So, most of the plasma which is coming from the sun is deflected and does not enter the region dominated by Earth's magnetic field. So, this is called as the magnetosheath. So, that is the reason that the solar wind plasma will simply move something like this. So, most of the plasma from the sun is deflected and does not enter the region dominated by Earth's magnetic field. This is how the magnetosphere is able to protect the planet Earth from these harmful highly energetic particles, all solar wind particles. So, we will discuss about more interesting aspects related to magnetosphere in the next lecture.